We've got some definitions that we need to look at before we actually start doing some of these problems. The first type of problem we're going to be working with are problems that are called standard maximization problems and in standard form. Now, our linear programming problem is said to be in standard maximum problem in standard form if its mathematical model is of the following. We're trying to maximize the objective function subject to problem constraints of this form where I've got less than or equal to type linear constraints. All my variables have got to be greater than or equal to 0. So these are type of problems that we've seen before back when we were graphing in the other chapter. Now, basic variables and non-basic variables. This will be your first encounter. We will look at these a whole lot more, believe me, and also basic feasible solutions. Given a system of linear equations associated with a linear programming problem, the variables are divided into two mutually exclusive groups as follows. Now, mutually exclusive means together they are separate. We have basic variables. They're selected arbitrarily with the one restriction that there may be as many basic variables as there are equations. P is always one of the basic variables. The remaining variables are called non-basic, and the non-basic variables are always set equal to 0. If the values of the basic variables are greater than or equal to 0, then the corresponding solution is said to be a basic feasible solution. So my solution has got to be greater than or equal to 0, pretty much is what this says. The fundamental theorem of linear programming. If the optimal value of the objective function in a linear programming problem exists, then that value must occur at one or more of the basic feasible solutions. And technically the basic feasible solutions actually go back to what our corners are or were. But the thing about working a linear programming problem using a matrix, we always do as well as, if not better. We really don't check all of the corners. Okay? In the first section, we've got some situations like this, or problems like this. So it says, listed in the table below are all the possible choices of non-basic variables for this system. And now, in each case, they want us to find the values of the basic variables and determine whether the basic solution is feasible. So, now if you'll notice, I've got 6 different ways that two of these 4 variables can be 0. So we're going to look at every one of them. So if x sub 1 and x sub 2 are both 0, then that means s sub 1 would be 50. S sub 2, if these are 0, would be 40. I'll worry about feasible here in just a second. Now, x sub 1 and s sub 1. I've got to look for an equation that has x sub 1 and s sub 1, this first one. And if x sub 1 and s sub 1 are 0, that means x sub 2 would have to be 50 in order for this to be true. S sub 2, well, let's go down here. X sub 1 is 0, x sub 2 is 50, and we're trying to find s sub 2, which we now can. So if x sub 2 is 50, that would make this 100, and if you solve for s sub 2, you should end up with a negative 60 on that. Okay? You might need to write these down to the side if you want to. X sub 1 is 0 and s sub 2 is 0. X sub 1 and s sub 2. So that means this one right here. X sub 2, I'll need to divide both sides by 2, so my x sub 2 would be 20. S sub 1, let's go right back up here. X sub 1 is 0, so I don't have to worry about that. X sub 2 is 20. So if I subtract 20 from both sides, my s sub 1 should be 30. Okay, let's look at this one. X sub 2 and s sub 1, that's this one. If x sub 2 and s sub 1 are 0, x sub 1 has to be 25. And then for us to find s sub 2, I know x sub 1, I know x sub 2, I can find s sub 2. So if x sub 1 is 25, subtract 25 from both sides, then that should be 15. What about x sub 2 and s sub 2? X sub 2, this right here. X sub 2 and s sub 2 are 0. So x sub 1 would be 40. Now I got to go to the first one. If this is 40, that would make that 80. This is 0, so I've got 80 plus s sub 1 equals 50. That would give me a negative 30. This one, when s sub 1 and s sub 2, when these two are 0, I've got two equations, two unknowns. Let's go do the RREF. So I have got 2, 1, 50, 1, 2, and 40. Second quit. And I have to check it, sorry. I'm not sorry. There's that. So second matrix over, let's go do RREF. For that matrix and see where they hit. So this would be 20 down here, 20 and 10. Okay. Now, is it feasible? Let's look right back up here. And it's this very last line. If the values of the basic variables are greater than or equal to 0, the corresponding solution is said to be a basic feasible solution. So what that means is all my variables have got to be positive. So this one would be yes. This one would be a no. Notice I've got a negative. This one, yep, it's okay. This one, it is alright. I've got a negative in this one. And this one is alright. So I want to change it. But that's what that means. I look and see because, guys, when we start doing these problems, for it to be a feasible solution, all my variables have got to be positive or 0. So I guess I could say if they're greater than or equal to 0. Okay? So if there's any negatives, I've got issues. And that's it for this video. Thank you.